Hello and welcome to the second video of the M3 chapter Further Centers of Mass. On the screen, if you've got time, a quick exam question to review the previous video's work. A uniform lamina occupies the region R bounded by the x-axis and the curve sine x. Show by integration that the y-coordinate of the center of mass of the lamina is pi by 8. We don't need to do the x-coordinate because by symmetry we already know that's pi by 2. So in the previous video, we had a lot of work based around this idea that x bar times the sum of the individual masses of a certain strip is equal to the sum of the individual mass times the x-coordinate of the center of mass of that strip. In this case, the strip we're taking is just the usual y delta x, where the center of mass coordinate is x y over 2. So the formulas we had in the previous video will apply unaltered, where we'll have x bar here, the integral of y dx to find the total area, and over here the integral of y times y over 2, so y squared over 2 dx, and I've put areas there to make those masses. We should really have rho, but we're going to cancel the rows anyway. So cancelling the rows and putting in sine x, we get x bar integral of sine x from 0 to pi is equal to the integral of sine squared x with a half in front dx from 0 to pi. On the left, that gives us minus cosine x 0 to pi, and on the right I'm going to have to change this into a half minus a half cos 2x, and then integrate, putting the limits in on the left. Cosine of pi is minus 1, so minus minus 1 is a 1, minus cosine of 0 is a 1, so that's minus 1, giving us 2x bar on the left. On the right I'm going to factorize out the other half there, make that a quarter, and integrate 1 to give x, and a minus cos 2x to give minus a half sine 2x. From 0 to pi. That's nice because if we put pi in here, that's going to be a 0, and if we put 0 in here, that's also going to be a 0, so it's just the x, and we get 1/4 pi minus 0. Rearranging, pi by 4 divided by 2 is pi by 8 for the x-coordinate of the center of mass, as required. In this video, we're going to find the center of mass of a uniform body, using a lot of what we did in the previous video, just applying it to 3 dimensions. We can apply all the ideas so far to 3-dimensional uniform solid bodies. This idea of being uniform is very important still. We'll come back to non-uniform in the next video. Firstly, we know that the center of mass must lie on any line of symmetry for uniform laminas. In 3 dimensions, this means the center of mass must lie on any axis of symmetry and on any plane of symmetry for uniform bodies. So we're going to look at some standard shapes where we can find the center of mass of a body just by using symmetry. Secondly, we can apply integration for a solid of revolution using similar methods to what we did in the previous video for laminas. So we'll look at some standard shapes first, and then we'll go on to the integration. For a uniform body, the center of mass must lie on any and all axes of symmetry and any and all planes of symmetry. So our first standard shape is going to be a sphere, although it looks very much like a circle. Imagine this is a sphere, and on a sphere we've got lots of different axes of symmetry, an infinite number of them. And of course they all cross at the sphere's center point. So the center of mass of a sphere is at its geometric center. For a cylinder, we've got one axis of symmetry that comes along the center like this. And we've also got one plane of symmetry through the center this way. And where these two intersect, i.e. the geometric center of the cylinder, is also the center of mass of this cylinder. Third and final one, a cuboid, very similar. The axes of symmetry and the planes of symmetry all intersect at the geometric center of the cuboid, and that is where the center of mass is. Each of these 3, of course, is relying on this word here. They are uniform. That means the mass is distributed evenly throughout the shape. So we've got some standard results there. We've got some more standard results to look at, but to get to those we're going to have to integrate. we can apply integration for a solid of revolution, just like we did in the previous video. It's all based around this idea that we had in the starter question, that the coordinate of the center of mass of the whole body times by the mass of the whole body is equal to the individual pieces' mass times by their center of mass. The difference here is that our piece is not going to be a rectangle or a triangle, it's going to be a disk. So on the shape here that I've got, this is the function along the top edge here, f of x, and we've rotated this 360 degrees around the x-axis to create a solid of revolution. What's important about this is that every point on this function, if you rotate that point about the x-axis, you will always get a circle. And this is the piece of the shape that we're going to use. I think it's fairly obvious that the center of mass of this disk is at the center of the circle, but we also need the mass of this disk. And if we have a disk of thickness delta x, then the volume of that, given the radius here is y, we can do pi y squared times by delta x. And then to turn that into a mass, we do what we did in the previous video, we multiply that by rho, where rho now is the mass per unit volume, and we can also call that density. So we're splitting our shape into many disks like this, each one delta x thickness and pi y squared area, which gives us this volume for each disk and this mass for each disk. So we can use this in here to sum these to find the total mass of the shape, and also we're going to put it in here, but we also need the x-coordinate of the center of mass of each disk, and we know that if the x-coordinate of the disk is here, the center of mass is just going to be x. So putting this in here and here with the x-coordinate as x gives us x bar sum rho pi y squared delta x is equal to the sum of rho pi y squared x delta x. Then you know what's coming next. We're going to take this to the limit where delta x tends to 0 and integrate. And to finish off, I will make x bar the subject, although you might have noticed in the starter question I didn't use the x bar as a subject version of the formula because I wanted to keep the integrations separate. I didn't want them all in one big fraction. But to have x bar as the subject of the formula, this will be the formula for the x-coordinate of the center of mass of this shape here. We don't need to go through this again for the y-coordinate, because any shape that is made by rotating a function about the x-axis will always have y-coordinate of its center of mass along the x-axis. So y bar will always be 0 in this case. Again, assuming that the mass is uniformly distributed. What we could do is do all of this again by taking a function and rotating it about the y-axis. And then you would find that all of this would just switch your x's and your y's around. So this would be y bar, y, dy, dy, x squared, and this would be x bar equals 0. And that would just be like taking this whole thing here and turning it 90 degrees around onto the y-axis. So we can apply integration for a solid of revolution to give the formula this about the x-axis and this about the y-axis, where all I've done there is change all of the x's into y's and all of the y's into x's. Similar to the previous video, you could, if you want, cancel those constants, but it might be nice to keep them in there because this is still representative of the total mass, and there might be questions where you know the total mass of the shape, in which case you might be using them as part of the mass and they won't then cancel in the numerator. Also, like the previous video, it might be worth remembering this if you find it easy to memorize formulas, but given that it's a very similar method to the previous video, if you know where it comes from, you can get to this formula fairly quickly from the M2 formula that we've been using throughout these two videos. This section also has quite a few examples, so if you're going to try all of them, brace yourself. First one, find the center of mass of the uniform solid right circular cone with radius r and height h. That seems like a lot of words to describe a cone to me, but I think they're just being very detailed there to make sure we get the right shape. So putting this on an xy coordinate grid, I'm going to have the line coming out like this to form the cone over here. We know the radius is r, and the height of the cone from O to the base here is h. That means the function that's being rotated about the x-axis to form this cone is this line here, with gradient r over h. So we've got y is equal to r over h x. And because this is a fairly standard example of what we're doing, we can just go ahead and put that into this formula. X bar is equal to the integral from 0 to h rho pi x times y squared, so that's r squared over h squared. X squared times x is x cubed. And for the denominator, very similar, rho pi r squared over h squared x squared dx. So these are all constants, so they cancel out very nicely, leaving us with just the integral of x cubed and the integral of x squared from 0 to h in both cases. That gives us x to the power 4 over 4 divided by x cubed over 3. Then putting in the limits gives h to the power 4 over 4 minus 0 over h to the power 3 over 3 minus 0, and simplifying that gives us 3h over 4. So the centre of mass along the x-axis here is 3/4 down from the vertex, or 1/4 up from the base. And just for completion's sake, let's remember that the y-coordinate of the centre of mass is 0. Second example, find the centre of mass of the uniform solid hemisphere with radius r. Again, onto our xy coordinate grid. We've got a hemisphere, so it looks like a semicircle there, but it's a solid shape coming around like this. The radius is r, so this is r up here and this is r here. Centre point at O. As a shape, this is also fairly standard. We're taking this function here, rotating it 360 degrees about the x-axis, so we can still use this formula. The difference here is our equation is slightly more involved. We've got y is equal to the square root of r squared minus x squared. We don't have to worry too much about that though, because we can see we're going to square that in both the numerator and the denominator. So for x bar, we get the integral from 0 to r of rho pi x times y squared, which is r squared minus x squared, dx, divided by the integral from 0 to r, rho pi r squared minus x squared, dx. And again, the constants cancel out, and we have to do the integration. In the numerator, we've got x times r squared, that gives us r squared x squared over 2, and minus x cubed, which integrates to give minus x to the power 4 over 4. Going from 0 to r. In the denominator, r squared gives us r squared x, minus x squared is x cubed over 3, and again going from 0 to r. I do like it when this happens. R0 is going to be a 0 in all of these terms, so we've just got the r to put in. That gives us r to the power 4 over 2 minus r to the power 4 over 4 minus 0. Just to make it clear for the examiner, I have put 0 in. R cubed minus r cubed over 3 minus 0. Putting these fractions together, we get r to the 4 over 4 divided by 2r cubed over 3, which gives us 3r over 8. 3/8 of r is just under halfway there. And again, just for completion's sake, state that the y-coordinate is 0. Example number 3. Find the centre of mass of the uniform solid of revolution formed by rotating the finite region enclosed by the curve x squared plus 1, the x-axis, and the lines x equals 0 and x equals 3 through 360 degrees about the x-axis. So this is our first non-standard shape. X squared plus 1 is something like this, and when we rotate that about the x-axis, we get something that looks kind of like this. And we're going from 0 to 3 on the x-axis, where y is equal to x squared plus 1. Again, if we think about our disks, nothing different is happening here to what we had in our derivation of this formula. we've got the disks here. The area of each one is pi y squared times by rho to give the mass, and then the centre of mass of each one is at the x-coordinate. So we're okay to go ahead and use this again. Before we put it in though, I'm just going to do a little bit of the algebra. We've got y squared is equal to x to the 4 plus 2x squared plus 1, so xy squared is equal to x to the 5 plus 2x cubed plus x. Now I'm going to put them in to give the integral from 0 to 3 rho pi x to the 5 plus 2x cubed plus x dx divided by the integral from 0 to 3 rho pi x to the 4 plus 2x squared plus 1 dx. And again, rho and pi cancel out nicely, and we get to integrate. X to the 6 over 6 plus 2x to the 4 over 4 plus x squared over 2. From 0 to 3, there's that nice 0 again. X to the 5 over 5 plus 2x cubed over 3 plus x from 0 to 3. Putting all of that on my calculator for the limits, we get 3 over 2 minus 0 and 3, 4, 8 over 5 minus 0, which gives us a final answer of 5, 5, 5 over 2, 3, 2. And again, y bar equals 0. As a decimal, that's about 2.4, which puts it roughly here. The next example is our first example that won't just use this. Find the centre of mass of the uniform hemispherical shell with radius r. So if I quickly sketch this out, here's our hemisphere, but in this case it is hollow. There is no mass inside, it's just a shell. And I would suggest that there are two ways to look at this. The first is the method used in the textbook, where they say here is a solid hemisphere. Let's cut out a smaller solid hemisphere to leave a little hole there, and then as we make that hole bigger, we eventually get to a point where there's just a thin shell left. And then if you call the radius of the original hemisphere r, and the radius of the small one little r, then you're taking the limit as little r tends to big R. The second option is to think of the hemispherical shell as concentric rings. Tiny, tiny little rings that we're going to add together to make up the shell. If you were to do it this way, you would have to be a little bit careful though, because you can't just take y is equal to square root of r squared minus x squared and expect to be able to find the area of this summing from 0 to r, because that's just going to give you the answer for a semicircle. What you need to do here is realize that because r stays the same as it goes around with increasing theta, that you can take a small section of this line and call that delta theta, and then rotate that about the x-axis to get the area of that tiny ring, and integrate from theta equals 0 to theta equals pi by 2. I think I'm going to stick with the method in the textbook in case anyone's read through that and needs a bit of help understanding it. Before I do though, a third option has occurred to me because of what we're going to do in the next example. Another way of doing this would be to split your shell into tiny pieces from here to the center point, little strips, and find the center of mass of each little strip along the surface, and because of the symmetry they would all be the same wherever they are, and you would end up with a ring of centers of mass wherever they were that would indicate the center of mass of the entire shell. The problem with that method in this example is that these are kind of triangular-ish as they come around here, but they're not really triangles because they are lying on a spherical surface. And I don't know where the center of mass of a triangle that lies on a spherical surface is. It will be a lot more helpful in the next example though, so we'll come back to that idea. So if we think of this as a hemisphere minus a slightly smaller hemisphere to give the shell as the final result, then we're not using this at all. We're going all the way back to M2 with our table, where we can say the big hemisphere minus the smaller hemisphere will give us the final shape of a hemispherical shell. I'm not sure how I can draw that and make it look anything different from a hemisphere, but this is a shell. So we take the mass and the x-coordinate of each, where this is going to be x bar. I'll use capital R for the radius of the big one, small r for the radius of the little one. The mass of a sphere is 4/3 pi r cubed, so the mass of a hemisphere is 2/3 pi r cubed, 2/3 pi r cubed, and here 2/3 pi r cubed minus r cubed. The x-coordinate of the centre of mass of a hemisphere we found from our previous example is 3/8 of r. For the small one, 3/8 of r. And then we do what we always do, this times this minus this times this is equal to this times this. If we multiply that, we get pi r to the 4 over 4 minus pi r to the 4 over 4 is equal to 2/3 pi r cubed minus r cubed x bar. The pi's all cancel out, and then to get x bar by itself we'll divide through by all of this, and that will give us x bar is equal to r to the 4 over 4 minus r to the 4 over 4 divided by 2/3 r cubed minus r cubed. I don't like having all of those fractions floating around, so let's change some of these numbers, and we get 3 r to the 4 minus r to the 4 over 8 r cubed minus r cubed. Now if we think about putting the limit in here, where little r tends to big R, we're going to get a 0 in the denominator, which is going to be a problem. So we're going to need to manipulate this expression to get rid of this problem in the denominator. A good first step here is to realize that this is the difference of two squares. So if I jump up here and rewrite that, we get r squared minus r squared plus r squared. And this is still r cubed minus r cubed. And then we can realize that this again is the difference of two squares, and rewrite that as r minus r plus r squared plus r squared. Now this still looks to me like a bit of a problem, because that will just give us a 0 overall. So I think this is a good bracket to try and get rid of by cancelling here, and that gives us a starting point as to how to separate this out. So if we force out r minus r in the denominator as well, to force those two to cancel, and we see what we get left as a quadratic here, we're going to need r squared and r squared. And then in order to make that true, plus r in the middle. Now this is looking really good because these two problem brackets cancel, and I can just go ahead and put in the limit little r tends to big R now and see what we get. So that will be 3. Here we've got r plus capital R giving us 2r, and then r squared plus r squared. So we've got 2r squared. In the denominator, r squared plus r squared plus r squared will give us 3r squareds. And then the r squareds will cancel, the 3's will cancel, and finally the 2 and the 2 there, making a 4, will cancel with the 8 to give us a 1 over 2, for a final answer of r over 2 as the centre of mass of a hemispherical shell. Penultimate example. Show that the centre of mass of the uniform hollow right circular cone with radius r and height h is at a distance 1/3 h from the base along the axis of symmetry. This example is a little bit strange, because the sorts of things we've done so far are quite complicated and there's a really easy solution. So let's go through the sorts of things we've talked about so far and see why they're complicated. The example we just had on the previous screen would have said, take a solid cone and then remove from that solid cone a smaller solid cone, and then a bigger one, and keep going until the smaller one reaches the limit of the bigger one. The difficulty here is that we've got two dimensions changing. We would have little r tending to big R as we did in the previous example, but we would also have little h tending to big H, and that just makes it a lot more complicated. Alternatively, as briefly mentioned on the previous example, you could use theta if I turn the cone around for this one, and you try to do theta here, theta here, theta here, from 0 to pi by 2, and you call this bit here a tiny change in theta, then the problem you have here is, unlike the hemisphere, you don't have a constant radius. This distance changes as theta changes, again making it a lot more complicated. Another way to do this, which is the way you will see in some other videos on YouTube, is to consider the tiny concentric rings, not dissimilar to the second idea, but in this case, going along the x direction, you've got to be very careful that here, instead of delta x, you've got a little delta L, where L is the slanted height of the cone. And either you could integrate in that direction, or you could still integrate in the x direction, but then you would need to consider delta L in terms of delta x, and you would find very quickly that you'd need a fixed theta for this. I found one or two decent videos on YouTube explaining this method, but all of that to say that the method in the textbook is by far the simplest. And this is the method that didn't quite work on the previous one, where I talked about having a tiny strip of the hemispherical shell, and it didn't work because that tiny triangle curved along a third axis. For a cone, however, you don't get that problem. There is still obviously a curved surface on a cone, but it's going around this direction only. Considering this direction, you've got a straight edge. So if we take a tiny slice of that surface area, and you can see we do have a curved edge down here, but if I call that a small part of the circumference, delta C, then as delta C tends to 0, this will approximate a triangle, and we know where the center of mass of a triangle is. It's 2/3 of the way down from the vertex. This didn't work in the previous example and does work in this example because the curved part of the shape becomes negligible as we take this to the limit, whereas in the previous example it didn't, because it didn't just have curved this way, it was also curving as it went up. The reason this is so useful then is because if we take another triangle on this side, and that's 2/3 of the way down, and you keep taking triangles around the entire surface of the cone, you get a ring of centers of mass all at the same height. And then using similar triangles, 2/3 of this distance we know is going to be 2/3 of the height in the center of the cone as well. Knowing, of course, that the center of mass must lie on that axis of symmetry down the center of the cone here. So if this height is 2/3 of h, then what the question is actually asking us from the base must be 1/3 of h. If you've got lots of time, do by all means try one of these methods, and I'm sure after 5 or 10 minutes you'll realize how much easier this idea is, specifically for a hollow cone. Our final example is still to do with cones, but it's not a full cone. We're going to look at a frustum. Find the position of the center of mass of the frustum of a right circular uniform cone of end radii 1 and 4 and height 7. Again, this is an example where we won't need this formula. We just need to remember our M2 work. First of all though, what is a frustum? A frustum, you might already know, is formed by taking a cone and cutting the top part of the cone off. So we're going to get rid of this part, and it's this shape here that's left over. We are going to need that top part of the cone to help us though. So putting that information on, we know that this is 4, we know that this is 1, and we know that this height here is 7. So I said we're going back to M2 concepts. We're going to take our table, we're going to have our full size cone minus the smaller cone, and that will leave us with the frustum. For this we're going to need the mass, and the orientation I've drawn it, we're going to be using the y axis, so the y coordinate of the centre of mass. In order to find both of these, for both of these, we're going to need to know the height of the original cone. This isn't too bad. If you remember your work on similar triangles, here we've got a big triangle, and here we've got a smaller triangle that's similar. So if I call this small distance here x, then 7 plus x for the full height of the cone divided by the base radius of the cone must equal x divided by 1 for the smaller cone here. Quickly rearranging that, we get 7 plus x is equal to 4x, so 3x is equal to 7, and x is equal to 7 over 3. That means the full height of the cone is 7 plus 7 over 3, 28 over 3. The mass of the big cone then is 1/3 pi r squared h, 1/3 pi times 4 squared times the height, 28 over 3. The relative mass of the smaller cone then is 1/3 pi times r squared, which is 1 squared, times the height, 7 over 3. The relative mass of the frustum is the big one minus the small one, 4 squared times 28 over 3 minus 1 squared times 7 over 3. For the centre of mass of these two cones, we're going to go back to the first example of this video, where we found it was 3/4 of the height down from the vertex, therefore 1/4 of the height up from the base. So for the larger cone, that's 1/4 of the height, 28 over 3, and for the small cone, it's 7 plus 1/4 of the height of the small cone, 7 over 3. The 7 plus there is just to get it relative to the origin. 7 plus 1/4 of the height. And of course the thing that we want, x bar. As I form the equation, I'm also going to simplify some of these numbers. So the first term becomes 3136 pi over 27 minus 637 pi over 108 is equal to 49 pi x bar. The pi's cancel out, as would the rows at this point if I had put them in, which gives us 441 over 4 is equal to 49x bar, for a final answer of x bar equals 9 over 4, which is the centre of mass of this frustum here. And only now have I realised that I've been using x and not y. It should be y bar, y bar, y bar, y bar. Everything else looks okay. Despite that slight mistake there, I hope all of these examples mean that you are now ready to try some of the questions in exercise 5b, and maybe I'll see you for non-uniform bodies in the next video.